Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial we're going to start our week of friction, and as you guys may have heard me say a bunch of times, friction is going to be the worst unit you guys can have. Now the concepts of friction are very simple. It's just draw a free body diagram, solve for the unknowns, and that's basically it. The problem with friction is everything has to do with the direction of motion, because depending on the direction of motion, that's how you decide which direction your frictional forces will go. And now for some cases it's pretty obvious. For instance, in this example you guys will see that there's going to be a box and it's going to be pushed on with a force. And we know that the direction of motion is going to be in the same direction as that force because that's what's pushing it. However, when we have cylinders, or especially when there's multiple cylinders, the direction of motion can sometimes be confusing. And if you get those direction of motions wrong, then the rest of the problem might be wrong because you're assuming a wrong direction, and then you'll have a negative sign, and then everything will start to mess up. So it's very important in friction to get the direction of motion correct, and it's very difficult. So it's kind of hard to explain, so the best way to do it is just show you guys an example. So let's begin. Alrighty, so looking at this example, it would like us to determine the smallest force P that must be applied in order to cause the 150, and it says pound, but we're going to switch that to kilogram because we're going to, again, keep everything in SI units. We're not going to go to imperial. You guys will never see imperial. But in order to cause the 150 kilogram crate to move, so this last part at the end is very important. We want to make sure that this crate moves. And then at the end it says that the coefficient of static friction, so this will be very important, between the crate and the floor is, and then its mu static is equal to 0.5. So that's going to be very important. Now before we begin, let's just go and do a quick concept of friction. So of course, if I have a floor, and I'm just going to draw a random floor like this, and I have an object on the floor, or a body, and I want to move it, of course there's going to be some friction. It makes sense. So if I'm pushing this crate, and I'll go into purple for this, if I'm pushing this crate to the right, so this is the direction of movement, this isn't the force, so this is how it moves to the right, we know that there's going to be a frictional force that counteracts this. So in this case, we'd have a frictional force going the opposite direction of the movement. So it's not always necessarily the opposite direction of the force, but it's the opposite direction of the movement. For example, the force that may be causing this crate to go in this direction could be something like this, a force like this, force P. So in this case, the direction of the force and the direction of movement are different. So that's why it's always very important that we look at the direction of movement when we're looking at friction, because the frictional force will be opposite to that movement. But now here comes the problem in friction is, well, we know that we have a frictional force F, so this is how I denote my frictional forces. It's just so I don't get it confused with this, which is how a lot of you guys will put a force on a crate. So I just want to, I clear that up by doing kind of a fancy F. Excuse me. So the problem comes is we know that there's going to be a frictional force in the opposite direction. The question then becomes, well, how do we find that frictional force? What is the magnitude of that frictional force? And it's very difficult to solve for, as you guys will see. But in this course, it's very convenient that all of our friction will be dry friction. So I'm going to write that down, dry friction. And what this means, which is great for us, is that the frictional force F is proportional to the normal force on the crate. So as you guys may have guessed, this crate, it's going to have a weight pulling it downwards, and then to counteract that weight, the floor provides a normal force on the crate going upwards. So this normal force will go like this, and this will be N. And what we're saying in dry friction is, depending on the magnitude of the normal force, we can calculate the frictional force. So what happens here is we say that F is equal to mu static, so mu S times N. And this is why that 0.5 is very important in this question, because it gives us a relationship between the normal force of the crate and the frictional force in the crate. What you guys will see in a lot of frictional problems is you'll have more unknowns than knowns, and if that's the case, you won't be able to solve the question. So to kind of help us solve these questions, we use this relationship between friction. Now, here's kind of one thing that we're going to have to keep in mind, though, is that F has three scenarios. We have a frictional force that's going to be greater than mu sub s n. We're going to have frictional force when it's equal to mu sub s n. And finally, when the frictional force is less than mu sub s n. And now, here's are the three scenarios for these. And these are very important to remember because the questions will tell you about these very specifically, and you guys are going to have to know which one to use. So, for something called impending motion, which I'm going to put right here, because this is the case of impending motion. Impending motion. Now, this is the case that you guys will see a lot, and the reason why is because it's the most convenient. F is equal to mu sub s n. So what this impending motion means is this is the frictional force that is going to be experienced by the crate the instant it begins to move. So if you go up and you have a question like this, and it says very specifically, what is the force to cause the crate to move? Well, then you're going to fall into this category right here, because the force required to just make something move will have that relationship right there, that impending motion relationship, which is very, very nice because it's just equal to something. The other two cases are a little bit more challenging. Starting with the top one, if our frictional force is greater than mu sub s times the normal force, well, what this means is the crate is sliding. And if that's the case, well, we don't know the frictional force. It's going to be something different. We have to start going into kinetics. And if our frictional force is less than u sub s times n, the crate is not moving. And this is very, very important because even though in this case we have one P on the, we have one frictional force on the crate and we have one crate, we can determine if it's not sliding or sliding. But let's say for fun we have put a second crate on top of this, like so. Well, then now we have to analyze a couple different scenarios. Scenario one could be is both crates move. However, scenario two could be the red crate moves while the purple crate stays stationary. And how do you tell if the purple crate stays stationary? Well, you look at this condition right there. You determine if the frictional force is less than mu sub s times n. If it is, it's not moving. If it's greater than, it is moving, stuff like that. And this is really it for friction. Friction is not actually a hard unit. It just can be very complex. And the reason why I think a lot of students struggle, and the reason why I struggled with it, is because a lot of it is conceptual. You have to kind of visualize the way things are going to move. And if you can visualize that, then you can start figuring out things like how the frictional force is going to go, which direction the frictional force is going to go. And that's going to be very, very, very important. Alrighty. So we're going to move on to the example because it's going to cover everything else I want to talk about. And that is this. When we have a crate, and I'm going to come down here and just, I guess we'll put some lines to show that I'm starting the example now. So when we have a crate, we have two possible scenarios. And I'm going to show you guys each scenario. And this is very, very important because a lot of students on the final will only check one of these scenarios. And if you don't check the other scenario, even though it's actually really easy, you'll lose a lot of marks. It's very important that you're going to have to check both. So we're going to have two scenarios. And each one of these is a crate, and we're going to put a force on it. Like this. So I'm going to switch to a kind of a red highlighter to show kind of the movement. So if I'm pushing on this crate like this, scenario one is the crate will just move. Like this. And this scenario is very, very easy. This one's called sliding. And this is the one you guys are all familiar with. You know, you push something, it'll start moving around the floor. Now, scenario two is a very kind of interesting scenario. And I'll show you guys how to analyze both scenarios. But scenario two, of course, if we have something that's very slender and we apply a load very, very high up, you guys can kind of see that instead of sliding, the crate will begin to tip like this. about the corner, about this bottom corner at the end. And this is called tipping. So if you're ever given a crate problem like this, you're going to have to analyze two scenarios, and it's going to be very, very important. If you don't analyze one of the scenarios, you're going to lose a lot of marks. The good news is both scenarios are actually very, very easy to figure out. You just have to get the free body diagrams right. And that's going to be all of friction. It all comes down to, do you have the free body diagrams right? If you do, it's actually just sum of the forces equals 0. You can solve for your unknowns. However, if you don't get the free body diagram right, well, the rest is going to end up wrong. So let's go down and let's analyze the scenario. So the first one we got is sliding. And this free body diagram is typically found to be the easiest. So what I'm going to do is I'm going to draw our crate. So we know that we have a crate that's just lying on the ground. And then the first thing I like to do is I want to put the load of the crate. What's causing this thing to move? Why is this a frictional problem? And if we look, there's a load being applied at the top corner, and it is going to the left. And we're just going to call this load P. And the reason why I applied this load first is because we can analyze, without the influence of anything else, how is this crate going to move? And it's pretty clear. And this purple, this isn't a force, this is just the direction of movement. We know that this crate is going to move, and where should I put it? I'll put it up here, to the left. If we push on this crate with a force going left, excuse me, the crate's going to move to the left. So right above this, I'm just going to put movement, because now we know which way the frictional force will be. Because remember, frictional force will always counteract the direction of movement. So if we're moving to the left, my frictional force between the crate and the ground must be going to the right. So it's going to be something like that. And then of course we have two other forces, and one of them is going to be the weight of the crate. So as you guys will see in frictional questions, most things are going to have mass, because mass is what drives the friction, because the friction is related to the normal force and the normal force is related to the weight. So it all kind of works out. So I'm just going to put this, and we're going to put W for weight. And of course, to counteract this weight, the ground is going to provide a normal force to the bottom of the crate. So I'm just going to come down here and put this as N. So if we look at this right here, let's try and figure out our knowns and unknowns. Well, the first one that we know for sure is the weight of the crate, because we said that the crate itself weighs 150 kilograms. And before I do that, I'm just going to dimension the crate. I can't believe I forgot. All good free body diagrams should have the dimensions of the body. So this one's going to be 3 meters, and the base of this is 2 meters. So something like this. And I'm going to erase the W, move down a bit so I don't run out of room. So the weight, we know, is going to be mass times gravity, and gravity is a constant, so all we need is the mass. But the question was so nice to give us the mass as 150 kilograms. So coming down here, the mass we're going to have is 150. Gravity, well, we'll use 9.81. I know in the midterm they didn't tell you which value of gravity to use. I'm not sure if we needed gravity for the midterm. I completely forget. But if you do need gravity, I kind of warn the other professors that we should include the value that we want you to use. So if it's included in the final, which it probably will be for friction, again, all friction problems usually have mass or gravity, something like that. I told them very specifically that we need to include it. But if you do this calculation, what you're going to get is 1471.5 newtons. So our weight's known. So if we look up at this, we actually only have 3 unknowns. So it doesn't sound too bad. The problem with sliding is that we only usually deal with 2 equations. Some of the forces in x equals 0 and some of the forces in y equals 0. Because the problem is, if we take moments, things will actually start to get messy. For example, if I were to take the moment right now, about this point right here at the bottom, where the normal force acts, where the friction acts, where the weight acts, what we'll see is we'll get that P is equal to 0. And well, we know P is not equal to 0, because this solution right now for sliding is for any case. P would be equal to 0 and we wouldn't have any movement. So we need to modify this to account for the fact that we want P to start moving. So for sliding, we're only stuck usually with two equations. Some of the forces in x equals 0 and some of the forces in y is equal to 0. So if we only have those two equations, well, then we have too many unknowns. 3 unknowns, we need 3 equations. But if we only have 2, then we can't solve anything. And that's when you guys are going to have to realize the fact that it says the crate is going to move. So remember, right in the question it said the force P that'll cause the crate to move. And the reason why I highlighted that, and it's very important, is because of that statement right there, we can say that the frictional force is equal to mu s times n. Okay, well that's great, because I know that us is equal to 0.5, so all this is equal to 0.5 times n. So if I know n, I now know the frictional force. Well, do I know n? Well, not right now. But we can easily take the sum of the forces, the sum of the forces in the y direction as 0. And if that's the case, what we see from our diagram is that we have the normal force going upwards and the weight going downwards. So n minus w, and all of that is equal to 0. Only 2 vertical forces, very, very simple to solve. So what we find out is that our normal force is equal to our weight. And we know that since our weight is 1471, our normal force is 1471.5 newtons. And then looking up at the equation above, we now know that our frictional force is going to be 0.5 of that normal force. So 0.5 times 1471.5. And that is going to be equal to 736 newtons. Perfect. So now if we look up, we did sum of the forces in y and we did friction. So our only equation left is going to be sum of the forces in x is equal to 0. And doing this, what we see is we have P going to the left, so we're going to have a negative P. And we got the frictional force going right, so plus F is equal to 0. Well, it's very easy to tell that P is going to be equal to F. So therefore, we can say P is equal to 736 newtons. So once P reaches 736 newtons, this crate right here is going to start sliding to the left. Now, this is one of the problems. A lot of students will get this answer of 736 newtons, and they'll say, okay, well, that's my final answer. Box it up, good to go. However, this is where they'll lose a lot of marks, because if we look up, we saw that there's actually 2 scenarios that this crate can do. One of them is sliding, and we know to cause that, P will be 736 newtons. However, there's that second scenario, which is tipping, and we don't know what amount of P is going to cause this crate to tip. So if we conclude that P equals 736 newtons, well, we may be right, but we also may be wrong, depending on what tipping is. So I can say that P equals 736 newtons, but I should put, highlighter instead of the marker, I should put in brackets that this is sliding. And I shouldn't box it yet, because that's not my answer, that's just part of the answer. However, I will have to compare this later to the final answer, so I'm going to highlight this so I have it for later. Perfect. So now when I look up and I have my P for tipping, I can compare and we can go from there. So I'm going to move on. We just did sliding. The second one's going to be tipping. And again, it's a different scenario, so we're going to have to draw another free body diagram. But before we draw this one, let's just kind of go to the mechanics of tipping. So if this is my crate, something like this, and we know that we're going to put a force on it in the top corner. So this is a different crate. It's going to be kind of the same scenario though. What we're going to find is this. It's going to tip about a corner. And this corner will be usually pretty easy to find. It's not going to be too crazy. but the crate's going to tip and do something like this. And here's what you guys are going to have to kind of understand. In this scenario right here, the only contact, once the crate starts to tip, the only contact the crate is going to have with the ground is at the corner where it tips at. So we see this corner? That's the only part of the crate that's touching the ground. Well, what does that mean? It means that this is the only location where the normal force will be touching the crate. So our normal force is actually going to shift towards the end of our free body diagram because that's the only place where the crate is actually making contact with the floor. So that's going to be very, very important. Now at the same time, a lot of you guys are going to say, okay, well that makes sense. I can see that. Nice picture. But if the centroid of the shape is over here, we see that the weight of the crate also shifts. And that's true. Once it starts tipping to this magnitude, the weight of the crate will shift and it'll start moving out. And then a lot of students will ask me all the time, okay, Clayton, I know the normal force is going to shift. So how do I find that shift? Well, here's kind of the good and bad news. The good news is you won't have to find that shift. That's great news. No one wants to find that shift. The bad news is a lot of students will say, okay, well, you're telling me I don't need to find it? Well, I don't believe that. Something's wrong. Why don't I need to find it? And this is the case right here. So this is my floor, and let's say that my crate just tips. Remember, I'm not interested in finding out when it tips where it's already almost on the ground. I want to find that exact instance it starts tipping. And at that exact instance, if it's tipping about this point right here, what we'll find is the bottom of the crate will be like this. It'll just barely start tipping. Remember, we want the exact instance this starts tipping. So if this is the case right here, as you can see, the normal force doesn't really shift. The weight. The weight doesn't really shift. It's still in basically the same location where it started from. But the normal force has already shifted to the end. So something like that. So we're going to have to very much so pay attention to that. So if we come down here, what we're going to do is we're going to draw the free body diagram for our crate for the second scenario. So we're going to have this coming across. Oops, I'm going to move this around. It's not looking too good. So I'm going to have this. So a lot of this is going to stay the exact same. Coming down here, I got P, which will come on my crate to the left, act on the left. So P, remember, we're just going to put the weight in the exact same spot it was before, because at the instance it starts tipping, there won't really be any shift. And again, we know that the weight is equal to 1471.5 newtons. And then here's the thing we're going to have to realize. Okay, so if we're pushing on the right side of the crate, well, it's going to tip about this left point right down here. So this is where we're going to put our normal force. Like this. And of course, we had friction counteracting it, going this way. So we have friction, our normal force with the weight. So all the forces will remain the exact same. The only difference now is the friction and the normal force have shifted over to the side. So finally, we need to just dimension everything right here. So this right here is going to be 2 meters, and the height of the crate is 3 meters. So something like this. And now for tipping, remember, think about tipping. If I have something that's very, very small and push on it, or not very small, but short, and push on it, it's very rare that that thing tips. If you think about something really, really tall, you guys will see that it doesn't take a lot of force to tip it if it's super tall. And that has to do with moments. As the distance of my moment arm increases, of course, tipping, the effect of tipping is also much more prevalent. So for tipping, and this is There's very, very few scenarios, but there are a couple, and I'll show you them later. But most of the time, the only time you'll ever want to use sum of the moment, most of the time, wheels is the other exception, but most of the time for crates, the only time you want to do sum of the moments is to find tipping. And what we're going to do is we're going to take the sum of the moments about I just call it 0.0, but basically the sum of the moments about the point at which the crate tips. Because it's in equilibrium, excuse me, because it's in equilibrium, the second before it starts tipping, we can say that the sum of those moments is equal to 0. So if we look at this, we see that we have P times a distance of 3 meters. And if we look at the rotation, it's going to be counterclockwise, so that's positive. And then the only other thing creating a force is going to be the weight. And the weight's going to be acting downwards, so it's going to create a counterclockwise moment, so minus W. And the distance here, well, it's going to be the centroid of that square, so it's going to be halfway in between the two sides, so it's going to be times 1 meter. And all of this is equal to 0. And well, some of you guys will ask, okay, well, I know a square that the weight's going to act right in the center. This is the same as distributed loads. But what happens if I'm given a weird shape? Well, we can actually find the point at which it acts, but that's next week, so please stay tuned. So what we're going to do is we're just going to substitute weight into this equation. So we know that the weight is 1471.5 times 1 is equal to 0. So basically it's just going to be 1471 divided by 3. So in this case, what we find is that P is equal to 491 newtons, and this is tipping. So now we're going to have to make a chart to compare. So I'm going to highlight this because just like before, this is a very, very important value in our question. Something like that. So what I'm going to do now is just kind of create a little summary. We've got P slide is equal to, looking up, 736 newtons. And P tip is going to be equal to 491 newtons. So if we look at this, and remember, when we're making something move, we don't start off high and then decrease the force. If we want to make something move, we start off low and increasing the force. So if we start at 0 and work our way up, what we see is that P tip is going to govern. We're going to hit P tip before P slide. So therefore, and this is always good to put a sentence, the crate will tip before sliding. And if that's the case, then we can say that our P, come on, work with me. Our P is going to be equal to 491 newtons. So don't forget the units. And we're going to just box this because this is now an actual answer, which is what we wanted. And I'm going to go red. Don't know what I was doing with purple. Makes no sense. And this is our final answer. And we're good to go. So that's kind of a very basic friction question. Key things to note. Free body diagram. Very important. Best way to find out is draw which way the things move. Show where the motion is. The second kind of thing, for a crate, check slipping and tipping. Usually students just check one, you'll lose a lot of marks. So please check both. But other than that, that's really friction, guys. It's all about drawing the proper free body diagram and going from there, and honestly just kind of hoping you get it right. So I think that concludes this example. Thank you guys all so much for watching, and I'll see you guys in the next video.